All right, we are in C++ world again with Stefan.
Stefan.
Stefan, who has a really excellent acronym for your name, which is?
STL. It's very convenient.
How convenient. Because we're in
As
C++.
foretold by the dark prophecy, as I like to say.
Interesting. So we met with you last time. We talked about TR1.
Mm-hmm.
And today we're going to focus on iterator debugging and safe SCL.
Secure SCL.
Secure SCL. Let's first start with iterator debugging. Give me the problem space.
So we've always had an STL, Standard Template Library implementation, going all the way back to VC6 in the Dark Ages. In VC 7.1, or 7 and 7.1, which was .NET 2002 and 2003, we made our standard C++ library implementation much more conformant. And so it started following the spec much more closely. In VC8, which was Visual Studio 2005, we again improved conformance, and we also added two features. And if you look on MSDN, they're called by the confusing names iterator checking and iterator debugging. And the fact that we chose these names is responsible for some of the confusion that exists around this. I like to call the features by the macros that are used to control whether they're on or off. So iterator debugging is controlled by the macro has iterator debugging. And because that's a mouthful, usually I abbreviate that to HID. So what iterator debugging does is the STL is very powerful in detecting problems as soon as possible. So you're writing some code and you need containers or you need algorithms. So you've got to store, a bunch of objects and you got to go perform some operation on them. Mm-hmm. The core functionality of most programs is like sorting and searching. Programs are always doing that. So you would use containers and algorithms for that. And many errors can be caught by the STL at compile time because it's all templates. So you write some code, you compile it, and if you've made a mistake, hopefully you'll get a horrible compiler error. Sure. Now, usually these horrible compiler errors are like 100 lines long, and they contain lots of angle brackets, and no one can understand what they're saying, and that'll be improved in C++ OX. But at least you get a compile error. Yes. It fails right then and there, before you ship the code, before you check it into mainline, before customers see it. So then you can fix it, even if understanding what the compiler is complaining about is difficult.
Sure.
Now, the problem is that not all errors can be caught at compile time. Some errors are fundamentally only catchable at runtime. And in the STL, these errors tend to be iterator invalidations. So an iterator is just a generalization of a pointer. For a vector, you can think of it as a pointer, although it's not really a pointer anymore. And suppose that you've got a vector of 100 objects. A vector is going to have all those objects contiguous in memory, just like a C array, just as if you had malloced up a chunk of memory or newed up a chunk of memory. Okay. And so you're happily random accessing the vector, hopping around, and then you start pushing back elements into it. So the vector is expandy. It'll start automatically growing. It has some slack space at the end. But eventually, as you push back elements, you're going to reach the limit of the memory that the vector currently has. You've made the size increase to its capacity. At that point, the vector has no choice but to reallocate. So it's going to allocate a new, larger chunk of memory, a geometric factor bigger. You can think of it as 2x, and our implementation is actually 1.5 times as big, which is a good compromise. And we're going to copy all the old elements from the tiny chunk of memory that we used to have to the bigger one that we just got. Then we're going to add your new elements at the end. So that way the vector is constantly getting bigger as you push back more and more elements, but it's always remaining contiguous, allowing you to do random access iteration. Now the problem is that imagine that you got a pointer or an iterator or a reference to an element in the vector, and then you started pushing back elements into it. Well, that's fine until the vector reallocates. When the vector reallocates and we free that old chunk of memory, your pointers, iterators, and references to the old chunk of memory are still around. So even though the elements are still in the vector, they've moved locations in memory. So what the standard is for this is saying that the pointers, iterators, and references have been invalidated, meaning they're still pointing and referring to what they used to, but the element's no longer there. It's picked up and moved. So if you try to use those iterators, pointers, and references, you'll trigger undefined behavior, meaning a crash if you're lucky, or horrible corruption of state, and then a crash later on, or mangling data.
Mhm.
Bad news.
Absolutely.
So with pointers and references, there's nothing we can do. They're built-in types. So from the library side, we can't detect anything. Theoretically, a very smart instrumented compiler could detect that stuff, but in the library side, we can't do anything. Now for iterators, they can be of class type. So we do have a hope of checking the stuff at runtime. That's what we did in VC8. We added this functionality, iterator debugging, and it adds this extra debug instrumentation to iterators that basically says, okay, you've got your iterator, and it points somewhere in a vector, you're dereferencing it. I'm going to go talk to the vector and see if the vector has reallocated since the last time we actually set that iterator to point into the vector. If it has, then instead of trying to read this garbage memory and corrupting data or something, I'm going to kill the program right then and there, and I'm going to pop up a nice little debug assert. So you actually get a message box saying, and the message box itself is confusing, so here's another area where people are confused by this stuff. But it's very helpful if you know how to interpret it. And by interpret, I mean ignore 99% of what it's saying. The title of the message box says something like, Microsoft Visual C++ Libraries debug runtime error or something.
2008.
Yeah, and often it'll have the version in it. And it sounds like the libraries themselves have a bug and it's complaining that, wow, Microsoft has screwed up. Actually, what the thing is telling you is that your program has a bug. But the message box is coming from the libraries, and that's why the title's there. And then it'll say the name of the program, and then it'll say debug assertion, or iterator debug assertion, or something like that. And then it'll have some custom text saying exactly what's wrong, like dereferenced invalid iterator, or array index out of bounds, vector index out of bounds, something like that. And then some more nonsense, and then it'll say abort retry, ignore, and then it's got some text that says if you hit retry, we'll actually break into the debugger and whatever, because we're using a standard Windows API to pop up this dialog. So the dialog is crummy. The core meat of it is that one sentence in the middle that says what exactly went wrong. Like, wow, you tried to index the millionth element of a vector that really only has 100 elements, or you dereferenced an invalid iterator. Once you see that, then you can go break into the debugger and see exactly where the invalidated iterator or whatever is dereferenced. Not some crash downstream, 100 instructions or 10 minutes later. So in that sense, it's a very powerful way to figure out exactly where the correctness problems in your STL code are. But the check is inherently a runtime. So it's an extra layer of debugging. Theoretically, you could try to work backwards from a crash that happened downstream, but it's a lot easier if the library detects it proactively.
So let's talk a little bit about it. I mean, from what I'm hearing, it sounds to me like it's not necessarily a problem 100% with the pattern of your code, in the sense that if this chunk of memory has been allocated for the vector, and the vector grows, and therefore you have to allocate a larger chunk of memory, which then repositions all the elements if you added new elements to it.
Yeah.
That's something that, I mean, that's bound to happen. And in my code, all I was doing was just checking for something. Yet, I should know implicitly that because I'm adding elements to this vector, that it's going to grow.
Yes.
And
you should be aware of invalidation. So if you've ever, the problem here is persistent iterators. It's okay. It's okay if you're just, say you've got some vector and you're constantly pushing back elements into it, and then occasionally you iterate through the whole vector. So you do the usual for vector int iterator I equals vbegin, blah, blah, blah. Or you could use our for each construct, which is an extension, to iterate through the whole vector at once. Because you're getting the iterators right then and there, you never have to worry about invalidation. You're always getting the freshest begin and end for the vector. The problem is when you get an iterator in a vector and then you go stash it in a variable someplace. If it's persistent, then it can be invalidated. And it's okay if the vector doesn't grow in between that. It's only if you stash that iterator away and then you grow the vector that you risk invalidation.
So let's talk about that. I mean, to me that sounds like a bad pattern.
It is a bad pattern.
Why would you store an iterator in a variable for a vector that's going to be dynamic in size?
Sometimes it's not obvious. Sometimes one part of code is finding an element and then storing an iterator to it, and maybe in a member variable. And then another method of the class will have reason to add elements. Maybe it's getting new data, and then later on we go use that stored member variable without realizing that it was invalidated. So in a single function, the problem is very obvious.
Sure.
But if you've got different member variables and member functions of a class,
Absolutely.
it might not be obvious, and that's where this extra checking comes in. So you should avoid it statically in your code, but having that extra debug check is definitely useful.
Sure. And of course, if you happen to have, a method that's being shared with another execution context, or a calling code comes in.
Mm-hmm. You're a library function or something.
Got it.
Yeah.
All right. So did you write this iterator debugger?
Actually, I did not. So
Okay.
I joined the team in January 2007, which was after we shipped Visual Studio 2005.
Okay.
We license our standard C++ library implementation from a company called Dinkomware.
Okay.
They're a small company that is dedicated to writing standard C++ libraries and some extensions.
Okay.
And they write a very conforming code, and historically we've just licensed our implementation and added some stuff onto it and made it work with /CLR and things like that.
Sure.
But they were the ones who implemented has iterator debugging. The story's a little complicated though, because in VC8 not only did we add iterator debugging, we added this iterator checking stuff controlled by the macro secure SCL. And that was all Microsoft. We actually implemented that in our code base, and there's a conflict there because some of the stuff it's doing is replicated by the stuff that iterator debugging is doing. And the code doesn't really know about each other. So there's some inefficiencies there. There have been horrible bugs in VC8 that we fixed in VC9. Now we're working with Dinkomware for VC10 to get rid of this conflict and have just a single implementation that has different levels. So you can have, super speed, you can have just iterator checking, or you can have the full-fledged iterator debugging, and you don't have these duplicate member variables, this duplicate checking, and these horrible bugs.
Absolutely. So, let's talk about it. So with iterator debugging, I'd like to focus in on how it actually works.
Oh, yeah.
And then talk about sort of what's the cost. Nothing comes for free. What's the price?
And in fact, it can be significantly expensive.
Okay.
So, iterator debugging. This is controlled by the macro has iterator debugging. And this is all in the most of this machinery is centralized in our internal header X utility. So headers with names like vector and map and whatever, those are specified by the standard. Those are for users. Our convention is that internal standard C++ library headers, actually Dinkomware's convention, are prefixed with an X or a double X. So if you see an X there, that means users should never be directly including it. It's just for the headers to include behind the scenes.
Okay.
So if you really want to look at the implementation, most of it's there in X utility.
Right.
And then it's there's other parts that are actually in headers like vector themselves. So the iterator debugging machinery, the simplest container is vector. It's a little more complicated for things like deck and map and set and list. Vector is the simplest one to understand. So suppose that you've got a vector, and say it's going to store some ints v. So v, its representation in memory is 3 pointers. And this is the simplest core representation, pointing to a block of ints. So 5, 6, 7. You've got your begin pointer, you've got your end pointer, and then, actually this would point one past the end. And then you've got your capacity pointer, I think that points there. And these map to the begin, end, and then the capacity of the vector. Every vector has got to contain these pointers, or a pointer and some offsets, but we use 3 pointers. And then suppose that you've got a vector int iterator I. And this could equal vbegin, or it might equal vbegin plus, say, 2, in which case it would point to the 7. So people often think of vector iterators as just plain old pointers. And in fact, in many STL implementations, they are plain pointers. So I would literally be an int pointer that would point to this element. In VC8 and beyond, vector iterators are never pointers. They are always of class type. This broke some people who had this non-conformant assumption that they were always pointers. And when you have iterator debugging on, its representation becomes more complex than a plain old pointer. Okay, so I is going to contain a pointer member that's going to point to the element that it refers to. It's also contain extra stuff, and the vector itself is going to contain some extra stuff. So imagine that you've got this iterator here, and then the vector later on is going to get some new elements. So you're going to push back some value. And maybe you do a lot of pushbacks, maybe you do some multi-element inserts. You're adding elements onto the vector. When the vector undergoes a reallocation, it needs to tell all of its iterators that they have been invalidated. Because if later on you say dereference I, this is a call to the operator dereference of the iterator. This expression doesn't know anything about the vector. So if the iterator is going to know that it's been invalidated, the vector has to tell it, or the iterator has to ask the vector. Now, there's many ways to invalidate iterators. Vector reallocation is only one of them. Another way to invalidate an iterator is to get an iterator pointed to some container, and then just destroy that container. Maybe it goes out of scope. Maybe you've got it in a shared pointer that went out of scope or was reset. Maybe you've placement newed it and then explicitly called a destructor. If that vector goes away and you keep the iterator around, the iterator's invalidated even worse than, exactly as worse, as if the vector had simply pushed back several times.
Yeah.
So the container might not even be there. So when the vector undergoes reallocation, or if the vector is being destroyed, it needs to tell the iterator. The iterator can't ask the vector because the vector might be gone. So what the vector has is an internal member called myFirstIter. And what we're building is a linked list, a singly linked list of iterators. So every iterator has a myNextIter, and it also has a, I want to say myContainer. Hold on, I have a cheat sheet. I can never remember the names. Oh, sorry, it's myCont.
Which stands for container.
Stands for container. I have a separate variable called the full myContainer.
Sure.
For clarity. And so what this looks like is that a vector will have a pointer to the first iterator that's ever created for it. Later on, if the vector gets more iterators, it's going to follow this list and add iterators to the beginning of the list. So if you create a second iterator, it's going to build the list here. If you create a third iterator, and so forth. So a vector knows how to find all the iterators that have ever been pointed into it. And this is very different from if the iterators are raw pointers. Then the vector would have no idea where they are. If an iterator then is destroyed, it knows how to get back to the vector and say, wow, remove me from your singly linked list. Now this has a severe performance cost. Not only are we making the vector larger and the iterators larger, that's not so bad, but walking the singly linked list can be extremely expensive if you have lots of iterators. So this does come at a significant cost. However, you get very nice correctness checks. So the vector is always keeping its iterator list up to date. If iterators are created, it's going to add them to the list. If iterators are destroyed, it's going to remove them from the list. And if the vector undergoes reallocation, it can walk its iterator list and tell these iterators, you're invalidated, you're invalidated, you're invalidated. I believe that just sets their myCont pointer to 0, which is a sentinel value. Then later on, if you try to dereference the iterator, it's going to look at its extra member variables and say, wow, have I been invalidated? If it has, then we'll trigger the iterator debugging check right then and there, and this would say dereferenced invalid iterator. It's up to you to find out how it got dereferenced, but at least we're telling you that it was dereferenced right then and there. So it should be very close to the actual problem.
Interesting. So let's talk about,
Oh, and also quantitatively, the performance impact is often not so bad, but in certain applications, it can be literally 1,000 times. These are applications that are doing very tight loops over vectors using iterators, often if the vector has many iterators around. You can always fall back to raw pointers with a vector. You don't have that option for things like maps and sets and lists. But for vectors, you can fall back to raw pointers if you need that speed. So sometimes people do want to turn iterator bugging off for the performance penalty. But the correctness checking is so useful that by default you should leave it on.
Well, I mean, which is what I was going to ask was, why wouldn't you do this in debug mode to ensure that your pattern is correct?
Mm-hmm. Well, iterator debugging is on by default in debug.
That's what I'm saying.
That's the good news.
But you don't ship in debug mode.
Exactly.
So this is not going to run.
It's not meant for retail, for your ship builds, because it's so expensive.
Exactly.
Yeah. But even in the best case, it's like 2x as slow for anything that's doing a reasonable amount of work with the STL. And that performance penalty would be completely unacceptable in retail. So this gets into the matrix of options that you can have with Secure SCL. So that would be, spread. You've got iterator checking. And this is controlled by the macro Secure SCL. SCL stands for Standard C++ Library. As far as I can tell, this is Microsoft speak. I'd never heard it before coming here. It seems like everyone else, and including the standard, will say C++ Standard Library, putting that first. And no one ever abbreviates it to SCL, whereas STL is very, very common. So that's just what that means. Now, the thing is, we do have iterator debugging and Secure SCL on by default, but we recognize that users may want their programs to go faster, or sometimes they can cause actual problems. There have been bugs in VC8. In VC9, we have fixed all known bugs with these, although some may lurk.
Well, you said all known bugs.
All known bugs, yes. The machinery is sufficiently complicated that I don't want to say, yes, we fixed all bugs. I guarantee I'll eat my hat that we've got them all, but I'm pretty sure we fixed definitely the worst ones. So there's a whole matrix of options, and this is the part that really confuses people, especially when they start trying to turn off Secure SCL. The story is actually kind of simple, although we've done a horrible job documenting it. You've got ship, and you've got debug.
Sure.
So ship is controlled by MT or MD. Debug is controlled by MTD or MDD. This is statically linked ship, dynamically linked ship, statically linked debug, dynamically linked debug. As an aside, no one should ever be playing with the preprocessor macro debug with an underscore. Failed its spelling. If someone tries to compile like this, this is telling the headers that they're in debug mode, but link against the retail libraries. This will produce horribleness if in fact it even tries to link. So these are the ways to select ship and debug. Debug is the case that we were just talking about.
Yeah.
Here we have both Secure SCL and has iterator debugging. So by default, they are both on. This is a part of the redundancy I mentioned. Really, iterator debugging supersedes Secure SCL, but because we implemented Secure SCL and Dinkmore implemented has error debugging, they can actually be configured independently. It's not too bad to have them both on, because error debugging is way more expensive, but it is a little extra bit of complexity. But users can customize these, turning one or both of them off. So you can turn off Secure SCL and have iterator debugging on. This one's weird. I don't know why anyone would want to do that. Or you can turn off iterator debugging to get extra speed. Or you can turn them both off for super speed, relatively speaking, in debug. The way that you enable and disable these guys is by defining these macros to 1 or 0. So by default, they're both going to be defined to 1. If you don't define anything, the headers will come along and say, wow, this macro hasn't been defined, I'm going to define it to 1, and then later on we condition on that. If you want to turn it off from the default, you would define Secure SCL to be 0. You can also do this in a preprocessed header file. And then you could also define has iterator debugging to be equal to 0. And that's how you switch either or both of them off. Now in ship, you only have the option to play with Secure SCL. Iterator debugging never applies to ship. If you try to turn it on by defining this macro to 1, the headers will politely ignore you. they detect that, wow, we're in ship mode, the users define this thing, I'm just going to undef it and define it to 0. So you can never have iterator debugging in ship. The machinery literally does not exist in the CRT binaries. SecureSCL, though, is by default on. However, you can turn it off for speed.
But not recommended.
Not recommended. So SecureSCL is a whole nother bag of worms. For iterator debugging, everyone should be... everyone seems to have a positive view of it because it provides these awesome correctness checks. Yes, it's expensive. We know it's expensive. Some people want to turn it off, but everyone agrees that it's desirable. With SecureSCL, there is large disagreement as to whether the thing is even desirable, and many people are unhappy that by default it's on. So what SecureSCL does, and again, MSDN doesn't explain very well the difference between checking and debugging. SecureSCL is a last defense against security problems. So it only applies to the case when you've got a program that's using the STL and it contains a security bug. What SecureSCL will do is it will detect a few cases where security bugs could be exploited through the STL, and then immediately kill your program dead. You don't get a nice dialogue telling you where the problem is in debug. It will simply immediately terminate your program. So at most you'll get a denial service rather than corruption of data or whatever horrible things attackers are going to do. In that sense, it's positive for security. But disabling it doesn't affect programs that are already correct. It's only a last-ditch defense. In that respect, it's like address space layout randomization or the GS buffer security checks, things like that. The difference is that SecureSCL has a significant expense. Something like the GS buffer security checks, they're almost free. Maybe 1%, you're almost never going to see it, it's in the noise. For SecureSCL, sometimes it can have a 2x or more performance impact. Now, the Microsoft line is this. We say that SecureSCL is cheap. Ordinarily, it shouldn't cost more than 5, 10%. Even in programs that use the STL heavily, if you're using STL algorithms, we will actually lift out that checking and then unwrap down to raw pointers, so we're avoiding doing repeated checks. Mm-hmm. So if you're consistently using STL algorithms, then you won't usually see a big penalty from SecureSCL. However, if you are working with iterators by hand all the time and your program is very dominated by tight loops that are working on STL containers, then SecureSCL can extract a significant performance penalty because we're replacing plain old things like vectors, array, index, and dereferencing an iterator with extra checks. That's extra branches, instruction cache pressure, things like that. Mm-hmm. So it can be expensive. Our line is that this improves security. Keep it on as much as possible. Do whatever workarounds you need to allow yourself to keep it on. Essentially the same thing that we say for iterator debugging. Mm-hmm. However, with SecureSCL, it seems that every external customer disagrees with us, especially people like game programmers. They take one look at this and they say, I don't need this expense. My program's already secure. Why are you making my program twice as slow? The STL should be fast. I want to turn this thing off. I have actually never met a customer who has said, wow, SecureSCL is the awesomest thing ever. Anyone who knows about SecureSCL seems to turn it off immediately. Now, the reason why it's on by default is because if it was off by default, no one would ever turn it on. And then the feature would be useless. And the idea here is that if a program had a security bug and it was exploited through the STL, then people would take one look at that and say, wow, Microsoft's STL was exploited, when really it was the buggy application. If we leave it on by default, what we're saying is that we're providing these security checks, the decision is yours. So if you say that your program is, has already been thoroughly security tested and the performance really matters, it's up to you to turn it off, and then the responsibility is on you. Mm-hmm. So that's why it's on by default. Personally, I'm in between. I don't know if I was implementing this from scratch, that I would make it on by default, because in general, I believe that programs using the STL should already be much more secure than their handwritten C counterparts. Mm-hmm. And I am somewhat uncomfortable with the performance penalty that it involves. On the other hand, I can see the argument that if it wasn't on by default, no one would ever bother to look through the documentation and turn the thing on.
Sure.
So I lean in the direction of, yeah, let's leave it on by default, which is what we do, and thoroughly document for power users and people who really care about performance that, yeah, you can turn it off.
Now, one of the cool things, though, you mentioned this earlier, is with the advanced work that's going on right in the same team on the Phoenix compiler, you could actually get some very interesting instrumentation results from compilation that could help you understand whether or not your specific patterns are incorrect. And you could, in fact, compose those checks yourself. So you could actually write.
I believe Phoenix can even do things like detect uses of invalidated pointers.
It probably can. So that's something to keep in mind. This is on the one hand, this is runtime security.
And this is the thing about this is it's all library only. So we have no interaction with compiler hooks and we work with the existing backend.
Sure.
So when Phoenix comes along, they're not, because if you have just a plain old, say a T pointer, maybe it's going to be the 0th element of the vector, and then later on you go dereference T. At the library level, we have no idea. We can't even see this because it's not doing any library calls. But Phoenix can come along and detect that, hey, this guy is bogus, just like we can detect that iterator dereferences are bogus. So it's going to increase our level of checking. I'm really looking forward to that.
Absolutely. That's really cool.
Yeah.
So, you know, the message here is use these things wisely. We always kind of say that, though. I mean, the idea
is that we have a same default that they're always going to be on, and that users, if they want, they can turn it off for speed. And again, you know, C++ is a language for experts. So if you're going to be modifying these switches that we provide to you, you should be knowledgeable about exactly what it entails.
Now, of course,
and in fact, it's actually much more difficult to modify these guys than it would seem from MSDN. And this is something that I'm looking forward to improving our support for in VC10. So earlier I mentioned the representation of a vector usually looks like 3 pointers. So this is plain. Under iterator debugging, it's got the 3 pointers, and then it's got my first iter. And under SecureSCL, again you've got the 3 pointers, and then it has a member that I personally added, this was in 9, called my owned aux. So imagine what would happen if you had a.cpp, which is compiled to a.obj, and b.cpp, which is compiled to b.obj, and then these guys are linked into some wonderful executable meow.exe. These guys both use vector, and when you're compiling a.cpp, you define SecureSCL to be 0. But in your build system, you miss doing that in bcpp. So ACP is going to compile fine, and when the headers try to define vector, they're going to recognize that, hey, the macro's off. I want the plain representation with no extra data members. I want the fastest, most obvious STL implementation possible. So this will compile just fine. When you compile B, you haven't turned off the macro. So the header doesn't know anything about this other translation unit that's been compiled. So you're going to get, say this is retail, the SecureSCL version, this extra data member. Then you try to link these objects together into an executable. If ACPP and BCPP have functions that call each other, maybe passing vectors around, then these vectors have different sizes. So you're going to get some horrible crash when BCPP tries to read a member of the vector that isn't there, that hasn't been passed. Essentially, something in ACPP would have pushed 12 bytes on the stack, and something in B would have tried to pop 16 bytes off. And that would lead to a horrible error to debug. Totally incomprehensible. This is a one definition rule violation. It's kind of our fault that we have these macros that make it so easy to commit ODR violations. Kind of our fault that we don't document very, very clearly in MSDN that modifying these macros can produce ODR violations, and kind of the user's fault for not understanding exactly what playing with the macros does.
Mm-hmm.
So the rules, which I've mentioned on VC blog posts, but can always be repeated, is that within a single translation unit, you need to define secure SCL, and a translation unit is a source file and all the headers that it includes.
Okay.
If you're playing with the macros, you need to define secure SCL and iterator debugging to 0 if you want to turn them off at the very beginning, before you include any standard headers. You definitely can't do include vector and then try to define your secure SCL to 0. That would be horrible. And then if you include another header, you might get vector with secure SCL off and map with secure SCL on. No one's going to be happy. So you definitely can't change it within a source file. Mm-hmm. Within translation units that are linked into a single binary, maybe an EXE or a DLL, again, secure SCL and iterator debugging must be consistent. If they're not consistent, you'll get a silent ODR violation, the one definition rule, meaning horrible runtime crashes, completely incomprehensible. You have no idea what your program is doing. And this is the tricky part. This also applies if you drag in a statically linked library. So suppose that you've got some C++ library, say Boost regex or something, that you're linking into your executable. If this is using the STL, then if you're turning off secure SCL in your own project, you also need to build these third-party statically linked libraries with secure SCL off. Or maybe this is first-party and you're simply building your own project as a bunch of statically linked libraries. Everything that goes into a single binary needs to have consistent settings or horrible bandwidths.
Now, again, that could be controlled by the build runtime. In other words, Phoenix.
Mm-hmm. Well, the idea is that the linker can see everything that it's combining into a single executable.
Absolutely.
So for VC10, what I'd like is just a little support from the linker, allowing us to have a pragma in the headers, saying, maybe pragma ODR, and I'm going to have, secure SCL is 0.
Nice.
And then in another header, I would say pragma ODR, secure SCL is 1. And so all the linker would need to do is see that, wow, I've got one translation unit saying this thing, another translation unit saying that this SCL equals 1. I don't care what SCL is, I don't care what the values are, all I can see is that they're different. I'm going to fail to link and tell you, wow, you've got inconsistency. That would give you a guaranteed check with only a little help from the linker and the libraries. And that would prevent this horrible class of errors.
Good. Well,
so that's something I'm
happens.
looking forward to in 10. Yeah. And now there is a third rule that users have to follow that we can't detect at link time, and that's if you have different binaries talking to each other. So if you've got, say you've got meow exe, and it loads kitty.dll, and they're talking to each other, they've got functions, exe is calling functions in the DLL, and if they pass STL objects to each other, they must have consistent secure SCL and iterator debugging settings. Otherwise, the DL is going to push 12 bytes on the stack, the exe is going to pop 20 off, and your program will crash horribly. You can have different settings in different binaries as long as they do not pass STL objects to each other. So if your DLL exposes a C interface or a purely COM interface, then there's no C++ signatures in its functions. Then they can have different settings. That's fine. That's actually a boundary, unlike the ones between translation units that go into a single executable. But if you're passing STL objects to each other, maybe this is boostregex.dll, then they need consistent settings or nightmare.
Now, but of course, you could do static runtime checking using some static analyzer or analysis tool that could detect the fact that you're passing STL objects between these two binaries. It could then alert you and say, hey.
In fact, you could just dump the exports of the DLL and say, wow, I see STL signatures in that. So that would be a little more advanced than we're thinking for VC10, but it would definitely be possible.
Sure. If
you could have all the DLLs and EXEs that you're loading on the disk at once and be able to look at them.
Yeah, I mean, and then of course, DLL, there's the term dynamic for a reason. It's a dynamic linking.
Yeah, if you load library, you don't necessarily know what EXE is going to drag in. So in that sense, the problem is really unsolvable. Turing complete. But
interesting.
If you have just the statically linked DLLs. In theory, we could look at all the DLLs that are loading.
Sure. Very nice.
Yeah.
So some new improvements, and again, the message here is use the debugger, the iterator debugger in debug mode, as well as secure SCL. Just do it, and then don't try to use those necessarily in ship mode, depending upon what you're doing. Clearly,
yeah. If your program, for example, our own compiler turns off secure SCL during its build, and that's an entirely reasonable choice. Now, within Microsoft, we do try to tell everyone, hey, keep it on. But for the compiler, it's got two concerns. A, speed really, really matters. And B, security is not a big consideration because people usually aren't compiling, totally foreign .cpp files, and those aren't attack vectors to own your system. So, because speed matters and because security is not a huge issue for the compiler, we turn off secure SCL, and the front end, which parses the language, uses the STL extensively, and it's getting super speed out of it. But for something that had a bigger attack surface and wasn't so dominated by CPU time, it would be more reasonable to leave secure SCL on.
So now let's talk about really briefly before we wind down. What are you seeing real C++ developers doing in the real world? I mean, not that Microsoft isn't the real world. So let's, we can talk about C++ developers like Raymond Chen or other guys in Windows or Office or wherever they happen to be. They're everywhere around the company. What sort of patterns are you seeing them use where you think that this could really help them?
Well, the biggest pattern there is people simply not using the STL. As far as I can tell, that's actually more widespread within Microsoft than outside. Outside, STL adoption seems to be pretty large. Within Microsoft, we do use the STL in places like the compiler front end, but it's definitely not universal. There's a lot of C++ without the STL using hand roll containers. There's a lot of plain old C still around, things like that. So the number one thing that those programmers could be doing to increase both the robustness and the performance of their code is to use the STL. The classic problem is that people who try to write their own containers are simply not as good at it as a dedicated library like the STL. The number one sin is, suppose that you've got an array wrapper, a vector imitator, and maybe it's storing some ints or something, and then you're inserting extra elements at the end. It seemed that whenever anyone writes their own array wrapper and they need to implement this expandy function to make the container grow, they decide, wow, I just need to, if I run out of space, I need to reallocate and add the original size plus some fixed number. For some reason, 10 seems to be extremely popular. I have no idea. And this seems reasonable if you don't know anything about library implementation, if you're not a hardcore library developer, because this doesn't have a lot of wasted space. At most, you've only got 10 slack elements at the end. The problem is that if you reallocate a container by any fixed amount, whether by 1 element, 10 elements, or 100 elements, whatever, and you push back a whole bunch of elements or insert at the end, you're actually going to have quadratic time complexity. Because you're constantly reallocating, you're actually going to do order of n squared element copies. And quadratic complexity is horrible. It's absolute death for any library. This has appeared more, it's embarrassing whenever it appears. It's happened like 5-6 times that I've seen within Microsoft. It's definitely happened outside. All because people are using these hand roll containers. Vector is smart. When it reallocates, it's going to reallocate geometrically. You're not guaranteed a particular constant here. You can think of it as 2n. We use 1.5n, which is pretty popular. If you use any constant here and multiply it, then you end up doing linear time if you're pushing back a number of elements. It's amortized constant time, meaning that occasionally we do copy a bunch of elements, but over the long haul, you can average it out, and you'll see that it actually is linear time. Linear is fast, quadratic is horribly slow. And that's just a performance problem that people run into. The other problems with handwritten containers is correctness. They're always buggy. If you're not even using a container and you're just using plain old, T pointers in C or C++, and you're newing up an array deleting or malloking and freeing, you're going to get your usual double free errors, memory leaks, things like that. If you simply use the STL, all of those correctness problems would be significantly reduced. Then you just need to worry about higher level concerns like iterator invalidation. Iterator invalidation isn't specific to the STL. It's a fundamental consequence of just having a container that can move elements around.
Sure.
So the reason why you don't often think about it in C is that you don't have containers that expand. It's so hard to have a chunk of memory and then reallocate and then copy all the elements over, which is why people usually suffer from C programmer syndrome, where they say, wow, I just need an array of 100 elements. No one will ever need more than 100 elements here, or max size, or max path, things like that. And inevitably, they do need more, and then the program has a buffer overflow, or it just fails, when an expandy container would have worked just fine. But the problem is still there. If you actually did reallocate, you would still need to worry about pointer invalidation. The STL simply surfaces that concern. But you only need to worry about high-level concerns like that. You don't need to worry about matching up your news and deletes. You don't need to worry about reallocating and being efficient. Vectors can do all of that for you. And then you can very easily plug it into higher-level algorithms. Like, I wouldn't want to see someone write their own sort, or their own, even their own binary search or something. They might be able to get it right, but they probably wouldn't make it as customizable as the STL.
Sure.
So use the STL would be my #1 suggestion there.
Absolutely. I mean, but then again, you know, C++ developers, you're one of them, like to have maximum control over the algorithm.
It's definitely not, the STL is definitely not a universal solution. It's a general purpose library. So it's going to be very robust, very fast, and very customizable. For wide majority uses, but there's no way it can possibly cover every single use.
Sure.
So there's always going to be uses where a handwritten solution will be faster, or do exactly what you want, or be even more robust than the STL. Maybe because you're writing a interface that's locked down to exactly what you need. So there's no chance of someone coming in and doing some other operation on your container. So it's definitely not, oh, you must use the STL everywhere. It's just that whenever you can use it, and it's the path of least resistance, you should. But if you need to go down to the bare metal, C++ permits you that option, and you should take it when it's necessary.
Absolutely. Fantastic. Well, hey, great to talk to you again.
Yeah.
STL.
Yeah.
Do people call you STL? Or
it's a lot more convenient than my whole name.
Yeah. Say your whole name.
It's Stefan T. Lauerwade.
Okay.
People are always mangling the first name, and the last name people take one look at and they say, I'm not going to try to pronounce that.
Right on.
So I can definitely understand why they would want to call me by my initials, and I hate typing the whole thing out, so I sign my emails with STL all the time.
And we can also understand why you're so strongly evangelizing STL.
I know, it's sort of convenient.
Very interesting. Well, hey, great to meet you.
Yeah.
Well, I've met you before, of course, but great to talk to you again. And keep up the great work.
Yeah, thanks.
All right, we'll be here again. Cheers.